Hi dear students, so let us come to the acceleration due to gravity of the earth. So the acceleration due to gravity, if you are considering the points or the heights which is near to the earth's surface, we are considered the value of gravitational acceleration constant g as a constant, that is 9.8 meter per second square. And now here we will derive the expression for the gravitational acceleration constant small g. Suppose if the mass of the earth it is me and the radius of earth it is re. We have to find out the force. For deriving the gravitational acceleration constant, we have to consider, or we have to find out the force acting between the earth and one of the particle which is placed at the surface of the earth, or which is situated at the surface of the earth. So for that purpose we will consider the earth as a combination of the particles of variable mass. So that the total mass me will be is equal to the mass of the fractions, that is m1 plus the sum of the mass of the fractions, that is m1 plus m2 plus etc up to mn. Then the force value will be is equal to F is equal to F1, that is the force acted between the particle of mass small m which is situated at the surface and the fractional mass m1 plus F2 likewise F3 etc up to Fn. So now you have to apply the inverse square law or the gravitational force equation, the equation for the gravitational force F, that is equal to G into M into me. Suppose if we are considering the gravitational force between the earth and another mass, otherwise m1 into m2. So G into me into m divided by the distance between the particle and the earth surface, means now you know that the gravitational force is a center force. So from center to center of the particles or the mass, you have to consider the distance. So from the center of the earth to the center of the mass, as compared to, it is the total distance will be re plus smaller is considered the smaller, it is the radius of the small particle. Here as we are considering the re and the small r values, where the radius of earth re will be very much greater than small r. Hence the re plus small r will be equal to, approximately equal to re. Hence the force value F will be become G into me into m divided by re square. Okay, so F is equal to G into me into m divided by re square. Now here we have to use the Newton's second law of motion, that is force value F is equal to ma. Here instead of ma, that is the acceleration a, we have to consider the gravitational acceleration. So F will be is equal to m into g, where m is the mass of the particle. Okay. So comparing, that is F is equal to m into g with the F is equal to g into me into m divided by r square, that is g into me into m divided by r square will become m into g, where on both sides the m will be cancelled and the gravitational acceleration value at the surface of the earth would be, or the expression for the gravitational acceleration value at the surface of earth will be g is equal to, that is small g is equal to g into me divided by r square, that is g, the gravitational constant value, into the mass of the earth me, all divided by the square of the radius of earth, that is re square. So g is equal to g into me divided by re square, that is the expression for the gravitational acceleration value at the surface of earth. If we are considering some heights which are negligible related to the radius of earth, there also the gravitational acceleration value will be g, or it is considered to be g. Okay. So here some points are given, that is the acceleration due to gravity does not depend upon the mass of the body m. That is very clear from that equation, that is the gravitational acceleration value g is equal to the gravitational constant capital G into the mass of earth divided by the radius of earth square. So here the small m value it is not specified, hence we can say the gravitational acceleration does not depend upon the mass of the particle. It depends on the distance of the place on the earth's surface from center of the earth. And the gravitational acceleration value it depends re. Suppose if the distance increases or decreases, then that means re plus, suppose a height h, then re plus h square. And as well, if we are going into a depth, okay, into the surface, if we are considering, then re minus d the whole square, that is the distance between the particle and the center of the earth. So the g will vary with the separation between the particle and the earth center. So we have to discuss how does this g value vary along with the height or depth. That means along with the variation in the distance between the earth center and the particle. So how does it vary below the earth's surface? So So you are having the G as G is equal to ME capital G divided by RE square. Now suppose at a depth D, the G of D will be there. G of D will be is equal to ME into G divided by RE minus D the whole square. Okay. So if you are taking the GD by G ratio, you know that ME G values will be get cancelled, and the remaining will be RE square and RE minus D the whole square. Okay. So as you are taking the ratio, you will get the relation, that is G of D is equal to, that is GD by G you have to take, then that will be is equal to RE minus D the whole square divided by RE square. By solving, you will get the relation, that is G of D, that means the gravitational acceleration at a point in a depth D inside the earth will be is equal to G into 1 minus D by RE. As you are opening the bracket, you will obtain the relation, that is G minus G into D divided by RE. So G minus a positive number, G into D by RE, where all the values are positive. So G minus a positive number means GD will be less than G. So gravitational acceleration inside the earth at any depth will be always less than the gravitational acceleration at the surface of the earth. Okay. So gravitational acceleration value inside the earth will be always less than that of that is the acceleration value at the surface of the earth. Now if you are considering a point above the earth's surface, so if you are considering it at a height h, then again there in the case initially G will be is equal to G into ME divided by RE square. Now G of H will be is equal to G into ME divided by RE plus H the whole square. That's RE plus H the whole square can be written as RE square into 1 plus H by RE the whole square. Actually this term it is at the denominator portion. So this 1 plus H by RE the whole square, as it is taking to the numerator, will become 1 minus of 1 plus H by RE the all raised to minus 2. Okay, 1 plus H by RE the all raised to minus 2. Then it will become 1 minus 2H by RE. This is a general relation, it is there, 1 plus x raised to n will become 1 plus nx if the x value it is very much less than 1. Here h is less compared to that of re value. Hence h by re will be very much less than 1. Hence 1 plus h by re the whole square can written as 1 plus 2h by re, and this re plus h square or 1 plus h by re the whole square, it is at the denominator portion. So as you are taking this one to the numerator portion, equation will become re plus h by 1 plus h by re the whole square. That is as it is taking to the numerator, this will become minus. So here x value it is h by re and n value it is minus 2. So this one become 1 plus minus 2 into h by re, that is 1 minus 2 h by re. Okay. Now you have to take the ratio between g of h and g. Then you will get the relation like this. That is g of h it is g into me divided by 1 plus h by re all raised to minus 2. If division it is there, then minus 2 will be there. Okay. So all square into re square. That is g of h value. G of h is equal to g into me divided by re square into 1 plus h by re all raised to minus 2. Okay. You know that g into me divided by re square is the small g value, that is the gravitational acceleration constant at the surface of the earth. So gh will be equal to g into 1 plus h by re the whole raised to minus 2, and using that relation, that is 1 plus x all raised to n will become 1 plus nx, as the x is very much less than 1. That relation you have to use here, then you will get the relation. This equation will become g of h is equal to g into 1 minus 2h by re. So that is g of h is equal to g minus 2gh by re. Hence here the gravitational acceleration at a height h will also less than the gravitation acceleration value at the surface of the earth. Okay. Now let us come to the concept that is the gravitation or the gravitational force. It is conservative force. So we have already seen that the conservative force is a force in which the work done will not be depending upon the path we have considered. It is depending only on the initial and the final points. And one more thing, the gravitational force it is acting central, and central force it is. So all the central forces are conservative forces. Hence, the gravitational force also will be considered as the conservative force. So now we have to find out the potential energy due to gravity. Potential energy due to gravity is actually the work done to bring a particle from one point to another point. That is the potential energy. And work done will be stored in the form of potential energy inside the in the particle. So here You know that the work done can be found in such a way, that is W is equal to integral of F dot dr. So here we are bringing the particle from a distance r to a very distance infinity. R to infinity you are bringing. So where the work done or the potential energy stored will be is equal to integration of r to infinity F dot dr so it become integral r to infinity g m into m divided by, so as we have taken the initial point as r, we will be taking the general term as r dash. Okay, here r dash into dr. So the equation will become minus g into m divided by r. So this is the potential energy stored in the case of the particle due to the gravitation. This is the general expression, that is where capital M is the mass of the earth and the small m is the mass of the particle. R is the distance between the center and the center of earth to the center of the particle. And one more thing, so that is the general equation for finding out the potential energy, that is G into capital M into small m divided by the R. So if you are considering a point very near to the earth, where the potential energy variation will be is equal to mg into h, that is h is the height from the surface of earth where the particle is situated. So on the basis of the general equation that we have derived now, that is g mm minus of g mm divided by the r. So initially the first one, that is the r plus h, that is the potential energy at the point h, and the second one, this is the potential energy stored at the surface. So this variation between them we are going to consider. So that will be is equal to g into m divided into 1 by r minus 1 by r plus h. Solving this one, you will get the m into g into m h divided by r square plus rh, as the h value it is very much less than r. This rh term will be get cancelled or negligible, and the equation will become m into g into m h divided by r square, where capital M is the mass of the earth and r is the radius of earth. So m into g divided by r square, that is m into g divided by r e square, that is actually the gravitational acceleration value. So at a height which is comparably very much less than that of the radius of earth, the gravitational potential energy has an expression, that is m into g into h, where gm divided by r square is g, hence m into gm divided by r square into h will become m into g into h. So that is about the gravitational potential energy. So the remaining portion we will discuss. So what you have to do is to read the textbook and as well practice the example questions and also the exercise questions. So just try to solve those questions as your own. And if you are having any kind of doubts, you can ask me. Okay, then we can wind up this session here. Thank you.